Okay, Chongyan, it's time to begin.
Okay. Let me share my slides.
Somebody sounds like they have a fan going in the background of their mic.
Okay, so can everybody see my slides? I'm still seeing your
Yes.
camera.
Yes, I see your slides. I can turn off my camera.
Okay. Okay, so we're gonna finish up the rest of part of this Newcastle. So the first thing after we see this kind of electrochemical behavior is we actually needed to like verify everything, especially the reaction sequence here. So first thing we do is using Raman spectrum, because Raman is very sensitive to like covalent band of like bromine and bromine chlorine. So we can actually use that, and we build up a homemade in situ battery to do the measurement. The thing is, we trying to use that to identify what's the reaction product during the charge and discharge at the different state of charge. So so before 50% of SOC, which is still in this within this first pattern, only thing only products we see is this kind of bromine intercalculant, and have no evidence showing that they still have the free bromines generated. So this bromine band is a little bit longer than the free bromine, mostly because when this bromine intercalculate into the graphite, it charge transfer happen between them, so it makes this interaction longer. So after 50% SOC, you will see the bromine peaks diminish gradually, and see another peak here is the bromine chlorine intercalculant showed up. And the interesting thing is, if we remove the filter of the Raman laser, which means we use a very high intensity laser beam to damage the material a little bit, you will see this free bromine chlorine gas generated. So that means it probably being de-intercalculate from the these kind of integration compounds. So which proves that even give us more proof that we propose the right reaction sequence. So the second evidence coming from the X-ray absorption spectrums we did in the in Argonne National Lab. We actually is another in situ measurement during the battery being charged. So before the 50% SOC, you will see this kind of bromine -1 being oxidized to bromine 0 state, but it will never reach to the real 0 state, just like liquid bromine, because because the charge transfer between the bromine and the graphene layers, right? So it will be reached to 100% of the 0 state after we fully charge it. So that's another mystery we will talk about a little bit later. But still, it proves the oxidation of the bromine. And another evidence comes chloride KH. So the chloride only being oxidized after 50% SOC, which means the second pattern, the chloride only being oxidized during the second pattern in the charge process. So there's another very interesting evidence coming from because we can actually decouple the amount of decouple the ratio of the active material and the the graphite, right? So what we did is we changed the ratio, molar ratio between the lithium bromide and lithium chloride we put in the cathode layer. In this way, we can see this kind of the capacities of these two platinums changing accordingly, which proves that the first platinum due to the bromide reaction and the second platinum due to the chloride reaction. And more interestingly, if we only reduce the amount of bromide, you are getting a decreased Coulombic efficiency. That's mainly because the solar chlorine molecular integration in the graphite is not so stable at the room temperature. So not as stable as like it has to be paired with the bromine atom to be stable. So that's another. So the second part is we trying to solve the trying to establish the staging structure of this integration reaction. And first thing we do is still using the synchrotron X-ray, XRD, to see this kind of involvement with the dominant peak of the with the d-spacing around like 3.35, which is yeah. So it's showing the involvement of the staging d-spacing distance between this integration gallery height. Interesting thing is the height keep expanding to until the 50% SOC, and it will decrease a little bit after the it's mainly the second platinum reaction platinum, right? That's mainly because in this stage you have chlorine integration, so the gallery height will decrease a little bit. And we do some ex situ measurement as well, and that brings us a lot of trouble because we actually don't know what happened. The reason is like Jeff showed a few years ago. This is, I think, is a PF6 interaction into the graphite. So normally this kind of interaction will bring us a huge evolution for the huge shifting and even spreading for the XRD patterns. But nothing like that happened here. So even Rivera think we did it very terribly wrong, and think maybe this kind of slightly shifting is due to the error during our measurement. But actually happened after we analyze that. It's correct, and it's a unique thing for the halogen integration here. So we did some calculation using the form factor and the dimension factor of the XRD, and the reason we think the shifting is the difference is so small is that because the bromine chloride the integration gallery height is around 7 angstrom, which means the half height, which is the interaction layer between the interaction layer and the graphene layer, is very close to the original height of the graphite, right? The 7 over 2 is like 7.5. So which means it can still keep the very similar pattern with the pure graphite, and the only thing happens here is a slight shifting due to the this kind of difference between the original height, d-spacing distance, and the half gallery height is like, which is 3.5 and 3.35. So with this calculation, we can actually do some compression here. So if we have like lithium integration, so for the staging 2, this is for staging 2 structure. For the lithium integration, you will have dominant peak showing at 0.02, And for the halogen, like bromine intercalation, for the staging 2, you are getting dominated peaks showing up 003. And for this kind of large alliance intercalation, like TFSI or PF6, it will show two dominating peaks with for the 0.3 and 0.5 at staging 2. So we actually have another very solid evidence to back up it. Is from Raman structure for the graphene for the Raman spectrum for the graphene structure, graphite structure. So the G band of the graphite is very sensitive to this kind of interaction structure. So if you're seeing the G band shifting to like 1612, it normally showing the staging 2 structure. And if it's shifting even more to the like 61, it was showing the staging 1 structures of the graphite intercalation. So the next thing we need to establish is in-plane structure, which I admit we didn't really do a very good job here. We didn't really figure out everything. But at least we first thing we figured out is the unique thing for the bromine or bromine chloride intercalation is the charge transfer between these atoms and the graphene layers is relatively low. For the bromine, it only have average like 60 16% of the charge transfer to the graphite. It's the number is way high, lower than the like alkaline ions intercalation and the this kind of large anions intercalation. For example, for the lithium ion, normally we think like 70 or 80% of charge transfer to the graphite layer, which is why we normally see the kind of goldenish color showing up for the lithium graphite intercalation after like stage 2 or stage 1. And for the large anions, because these kind of anions like PF6 or like aluminum chloride or TFSI, it cannot be oxide again. So which means like almost 100% of the charge transferred to the graphite layer, which means the graphite will be highly oxidized. So that actually give us a very good advantage here because if you have like very close to 0 state of these bromine and chlorine atoms, which means the repulsion between these atoms is relatively very low. So I think that's why we're getting this kind of high, most compact interaction compound we achieved here. Another thing is for the in-plane structure, we're trying to figure out if there is still have the like long-term ordering here. So we try to align all these kind of graphite flakes vertical to the X-ray beam, and we actually see this kind of peaks showing the long-term ordering, but it's rather very I think it's still still get a huge amount of disorder here, but we didn't actually have this kind of capability to analyze that. The only thing we can establish here is by the DFT calculation, we figure out this kind of interaction in-plane structure have this kind of zigzag building blocks. So with this model, the only thing we can do here is with this model to fit with our extended X-ray absorption spectrum, and trying to, actually it fits very well to give us a few most nearest bond lengths. Like for the bromide is the closest one is 2.5 angstrom, and we have a second set of like second nearest set is around 3.15, and rest of them is rather damaged, and we still can get to the bromide chloride distance here. So I think this building block is solid. So we it should be exist in the real compound. But I believe we need to spend more time to working on this implant structure, real implant structure, because I believe we have a huge amount of disorder here, and even we probably have multiple phase existing in this kind of cathode, fully charged cathode. But we still need to study that in the future. So that last slide is Jeff gave us a very generous comment, which I think we still have a lot of issues with this cathode we need working on. But at least I agree that this cathode is a very significant funding, at least for the in the view of scientific research, and I think it makes us think that make us think that maybe there still have other choice for us to discover for the high energy or low cost cathode materials in the future. So, so is there any questions left? We can discuss a little bit.
I have a question on the previous, no, on this slide here, yeah.
Okay.
So the X-ray pattern, the angles seem incredibly small. 2
Yeah.
theta, 1, 2, 3, 4 degrees. This is a very short wavelength synchrotron experiment, I guess.
Yes. It's a very high energy X-ray beam. We did it in Argonne National Lab. They normally have a very hard X-ray there, so we have to do a very small angle.
And was this in an in situ X-ray cell, or was this just a sample outside of a cell?
This is actually the X-ray situ. We take out the cathode to measure that, to try to enhance the signal. But for this one, it's an in situ measurement. And this one is the X-ray situ.
Okay.
But this one is not from synchrotron.
Yeah.
I have a question. Can we go to the previous slide?
Okay.
Yeah, so here it seems to show that, you know, as you're charging to 50%, then the bromine kind of is filling first. Have you guys ever tried to change the ratio of chlorine and bromine like you guys did with the capacity experiments and try to look at how the how it would fill up if there's different ratios of atoms in there?
Yeah, I know what you mean, but we unfortunately we didn't have this kind of beam time to do that. But I believe this arrow can actually show partially show that, because even with this area should have the different ratio between the bromine. Actually bromine is being fixed, and the bromine carbon ratio is being fixed, but still the bromine chloride ratio is still increasing, right? But apparently we didn't see a huge shifting here. So I don't know what happened. We probably need to study the staging structure even more in the future, I guess.
Yeah. So my question, I guess, is this behavior based on the occupation percentage or based on the different atoms? Like, say we had more chlorine than bromine, like would we start seeing a similar despacing once the chlorine starts going in the whole time, or
I think
it keeps opening?
Yeah, that depends on the different ratio of the different atoms. So it was shifting between, I guess it's shifting between the pure bromide interaction and the pure chloride interaction, which is, I guess, is between 7 to 6.8, I guess, as I remember that right. So there won't be a huge difference between the bromide and chloride.
Okay, thanks.
Gallery height.
Quick question. You mentioned the charge transfer from the graphite to lithium as well. What was the number? I just didn't catch that.
They still have some kind of debate. So mostly between this kind of people doing calculations. So most people think I think most people believe it's 0.8, 80% of the lithium charge being transferred to the graphite. So some people even say the 100%. It's like this large anion integration, but I don't really believe that, because we didn't see any kind of color change of I think some people also do the function, like work function measurement, but that technology is highly limited by the our samples. So, but yeah, but
Okay, so 80%.
80% is possible.
Okay, thanks.
Okay, then. Thank you, Chong-Yin.
Thank you all.
So that was very interesting. So now we'll move on to a horse of a different color, which is flow batteries. Okay, can people see my screen?
Yes.
Yep, we can see your screen.
Okay, good. All right, I want to start with my document camera, I guess, just based on the fact that it says, write the common types of flow batteries on the board. So we'll go to my document camera, hopefully. My goodness.
We can see your document camera.
Good. So can I now. All right, so a redox flow battery has two main things that are important. One is the electrolyte, and the other is the active molecule. And there's 4 different types of flow batteries. You can have an aqueous electrolyte or a non-aqueous. And the active molecule can either be inorganic or organic. So you can combine anything together that you want here. So you got 4 different types: aqueous inorganic, aqueous organic, non-aqueous inorganic, and non-aqueous organic. There's advantages and disadvantages to all of them, which we'll talk about as we go along. All right, so I want to start by just sort of showing that flow batteries are a thing that's happening today. So this is an aerial view of a factory in Dailin, China, that belongs to Ronki Power, and it produces vanadium redox flow batteries. The last information that I have, which is from their website, claims that they're producing about 3 gigawatt hours per year of cells. So this is a gigafactory. It's not as big as the Tesla gigafactory of about 35 gigawatt hours, or a CATL gigafactory of about 60 gigawatt hours, but it's still in the gigawatt hour range. This is a view inside their factory where flow batteries are being produced. This again is from their website. And these were batteries that are destined for an 800 megawatt hour storage station. This is from their website, specifications of their system. I compared this slide with the slide that I extracted from their website in 2019. it is exactly the same. So in 2021 and 2019, no specification of any of their devices has changed at all. They're all exactly the same. Okay, so some of the things that are interesting here is to look at the energy storage capacity of these modules. So here's a 200 kilowatt hour module that can provide 50 kilowatts. So that would be a C/4 discharge. They have 500 kilowatt modules that have different amount of stored energy. Maybe you want a 6-hour discharge, then it would be 3 megawatt hours, for example. They tell you the voltage and currents in AC. They have DC to AC converters on them. Don't get confused and think a redox flow cell operates with alternating current. You can see the temperature range. These vanadium redox flow batteries, by the way, are aqueous electrolyte and inorganic active material. So the operating temperature is between 0 and 35. And this is the thing that's most important to take note. The efficiency is between 65 and 75%. And we'll learn as we go along why the efficiencies are so low. Cycle lifetime greater than 10,000 cycles. We'll see another manufacturer in a few more slides that gives us over 25,000 cycles and over 25 years of life. So if these numbers are true, the lifetime of these vanadium redox flow batteries is very long.
Jeff, can I just confirm the efficiency? Is that energy efficiency?
Yes, that's energy efficiency.
Okay, thanks.
Here's a photo of a redox flow battery outside San Diego in California. This can store 2 megawatt hours. The media doesn't know the difference between power and energy. You don't store megawatts, you store megawatt hours. This came from Sumitomo Electric. This is a more recent, just taken a day or two ago from the same website where they're talking about this project, and you can see these redox flow batteries are the size of shipping containers with climate conditioning on top. 2 megawatts and 8 megawatt hours. Okay, so it's 8 megawatt hours, 1,000 homes for up to 4 hours. So then they're going to see if they can power microgrids with this thing. This is another company, VRB Energy. We'll see some spec sheets on there, I think, in the next slide. So 500 megawatt hour storage system at 100 megawatts, so C/5 discharge, 1 megawatt hour, 250 kilowatt hour. Oh no, 1 megawatt and a 12 megawatt hour, so C/12. China has a lot of vanadium, a lot. So there's a lot of motivation in China for making vanadium redox flow batteries. And down here, they're talking about the giant project that Ronki Power is involved with, the 800 megawatt hour vanadium redox flow battery. So here's a spec sheet from VRB Energy. Some of the most interesting things here are the DC efficiency here is listed at 80%. And when you do the DC to AC conversion, both in charging and discharging, you get 70% AC overall energy efficiency. So that's not so bad. Here's the most interesting one, 25 years of calendar life and 25,000 cycles. It says minimum value. So very impressive cycling. So I just wanted to spend a moment comparing these big vanadium redox flow batteries to some big lithium-ion battery storage projects. There's one in South Australia outside Hornsdale. This has been upgraded and made larger in the meantime. It's 129 megawatt hours. I think it's over 200 now. This is a system that's going in Moss Landing in California. It's going to be 730 megawatt hours with 256 Tesla megapacks. It'll be at C over 4, and they can expand this thing to 1.2 gigawatt hours. So a lot of big lithium-ion storage facilities going in as well. In China as well, 720 megawatt hour lithium-ion grid storage project in Gansu happening. Okay, so now let's try to understand why we would want to do a vanadium redox flow battery anyway. So this is a table from a big review article by Maria Skilakazakos. And it's a very good article. It's from 2011, but all the chemistry of redox flow batteries in that article are fine. But this table is somewhat dated, but what's nice about it is they give you a lot of different energy storage technologies here. Pumped hydro, superconducting magnet energy storage, compressed air, flywheel, supercaps, blah, 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 sodium, sulfur, lithium ion, and then finally flow batteries at the bottom. And they talk about the discharge duration in hours. So this just means how large would you scale the battery so that it can provide energy for a long period of time if you like. You know, so here they say lithium ion, the discharge duration would only be 1 hour. Well, you could obviously scale the battery to give you any discharge time you want. Just the question is, do you want to pay for so much battery? Flow batteries, they say, go between 1 and 20 hours. And then they start to talk about efficiency. So lithium ion greater than 90%. Flow batteries between 75 and 85. So I don't know how many flow batteries reach the 85% mark. You can tell the Ronchi Power vanadium redox flow were 65 to 75. So maybe 85 is at the high end. These numbers are very dated. Look at lithium ion costing between $850 and $5,000 a kilowatt hour. Flow batteries between 180 and 250. When we do our cost analysis later, we'll see that vanadium flow batteries have come down some from this, but not too much actually. So lithium ion will beat vanadium flow on costs. Cycle life.
Hey, Jeff.
Yeah.
So I don't understand the discharge duration, because you can control how fast or slow you discharge any battery, right?
Yeah, that's right. They're just saying that if you want to have, say you wanted to have lithium ion, that's a 20-hour discharge. Okay. So say you wanted a megawatt for 20 hours of discharge, then you would need 20 megawatt hours of batteries, and maybe to want to pay for that. Maybe it's too much money. Whereas if you only wanted a megawatt for 4 hours, you only have to buy 4 megawatt hours worth of lithium ion batteries. Maybe you can afford that. So the longer the discharge time, the more capital you need to spend buying the batteries. So if the batteries are super expensive, then you don't want to go for very long discharge time because you need a lot of them. That's basically
So discharge time is a financial metric.
Correct. It's a financial metric. Yeah.
Okay.
Okay, so then they talk about safety issues here. Fires and explosions for lithium ion. These redox flow batteries, they definitely have chemical handling, pumps, possible leaks. And, you know, you got to have parts for pumps, disadvantage compared to the other ones. The only disadvantage for lithium ion, apart from potential fires, is listed as high cost.
Hey, Jeff.
Yeah.
Is vanadium toxic, or does it have any, like, I guess, adverse environmental impacts, or no?
Vanadium dust is definitely a respiratory hazard. No doubt about it. You have to have very low airborne vanadium dust levels. Okay, so there's a number of things that I use to make this lecture. The electrochemical potential series is where all these redox potentials come from as we go along. Craig Horn is a guy that worked for a company called Enervolt that made iron chromium flow batteries. He sent me a presentation that I've stolen a few slides from. Michael Aziz is a very famous researcher at Harvard who's doing some of the best organic redox flow work in the world. This is the big, massive review article that I mentioned by Maria Skilakazakos. It's really quite a good review article on flow. And then there's some more modern papers on on organic redox flow batteries by Chen and Rowe. This paper by Darling is a really nice economic analysis of redox flow batteries. And a co-author in this paper is Kevin Gallagher, who now works at, I can't remember if it's BMW or Bosch, but one of those two German companies.
BMW, Jeff.
Okay, BMW. And a lot of random things from the internet and then my own experience. Okay, so what's interesting about a redox flow battery? So what you have is an electrochemical reactor here. So there'll be a porous electrode, usually carbon fiber paper. And that carbon paper is where the charge transfer takes place from the ions in the electrolyte to the electrons coming in the wire. And there's a pump that circulates the negative electrolyte through a storage tank, through this area by the electrode. This is just continuously running. And you have the same thing happening on the positive side. So if you want to store more energy in a redox flow battery, all you have to do is increase the size of the tanks. If you want more power from a redox flow battery, you have to increase the size of the electrochemical reactor. So it's kind of interesting that you have this separation between energy, the tanks, and power, the electrochemical reactor. So it's very different than a lithium-ion battery where the size of the cell controls the power it can deliver and the energy it can store. Whereas here you have this nice separation. So this is one of the reasons that people talk about flow batteries, you know, being well suited for long discharge times, because you can just put on a bigger tank, which really isn't that expensive. So like I mentioned, you can have different types of flow batteries, and we'll talk about all of these as we go along. So this is a slide that comes from Craig Horn at Enervolt. And again, if you're doing an aqueous flow battery, you have to worry about the limited electrochemical window of water. And what Craig Horn says, it's better to pick an electrode couple that's lower on the potential scale than higher, because you can tolerate hydrogen generation. It's reversible and it doesn't really degrade the cells, but oxygen generation is reversible, but it degrades cells because you can have oxygen reacting with organics to give CO2, and that's can be irreversible. So in general, people are trying to work lower down in the electrochemical potential table as opposed to higher up. So the vanadium redox flow battery works on vanadium 2,3 at one electrode at the negative and vanadium 4,5 at the other. So these are some of the reactions of interest for us in the iron chrome flow cell. You have at the negative side chromium 3 getting reduced to chromium 2 minus 0.42 volts back and forth, and iron 3 getting reduced to iron 2 and back and forth at 0.77 volts. So you can take the difference between these two numbers and realize it's about a 1.1 volt cell roughly, maybe 1.2 volt cell. And in the vanadium flow cell, vanadium 3 gets reduced to vanadium 2, goes back and forth. And then you have this ion here, VO2 plus, so that's vanadium 5. And it gets converted to VO2 plus. So this is vanadium 4 at 1 volt. So this is the 2 to 3, and this is the 5 to 4 reaction taking place. Wait a minute, this is not vanadium 5, is it? This would be
It should be 5.
yeah, this is
I think the
5.
other one is
minus
6. 5 to 6.
This is 5. And this is, that's 2 minus, this is 4. This has to be vanadium 4.
Oh.
Right? 5 to 4. Okay, so let's talk about how the vanadium flow cell works. So it's kind of cool to see the actual reactions that take place in it. So you have a porous carbon positive electrode and a porous carbon negative electrode. And then the fluid that flows past the electrode is called the catholyte. And the fluid that flows past the negative electrode is called the anolyte. So it's the electrolyte with the positive electrode active species is the catholyte. And separating the two is a membrane that prevents the flow of fluid, but allows the passage of ions. And if it's Nafion, it allows protons to pass through it back and forth. So Nafion is a proton conducting membrane, and we'll learn a lot about it when we get to the fuel cell section in probably next week. Okay, so what happens here? So first you have to prepare the solutions for the catholyte and the anolyte. So for the catholyte, you have V2O5 dissolved in sulfuric acid, and we have to see what that turns into on the next slide. And this turns out to be about 2 molar in vanadium and in protons dissolved in sulfuric acid. And the anolyte is an electrochemically reduced solution of vanadium 3 plus in sulfuric acid. And I'm not sure how this is made. This is easy to make. You just dump V2O5 and sulfuric acid and you make this stuff. I don't know how this is made. And that would be the fully discharged state. So this explains what happens when V2O5 is added to a suspension of V2O3 powder. The vanadium-3 ions in solution electrochemically leach the V2O5 powder, causing it to reduce to the more soluble tetravalent state that dissolves in solution according to 1/2 V2O5 plus V3 plus H plus 2 VO2 plus 1/2 H2O. The vanadium-4 solution thus prepared was electrolyzed to vanadium-5 in the positive half cell compartment of an electrolysis cell. So this is the way that you make the VO2 plus. Okay, so let's find out what happens here. So on the positive side in the catholyte, you start with VO2 plus. You have sulfuric acid around. And in the negolite, you have vanadium-3 plus, also in sulfuric acid. So when you charge the cell, you have to figure out what is happening at the different electrodes. And you connect the circuit, right? Because the electron flows through the external circuit. So let's see what happens. On the positive side, this VO2 plus and a water molecule. You strip an electron off of this. So now you have 3 positive charges because you've removed an electron. And now you get VO2 plus. So this is vanadium-5. This was vanadium-4. Vanadium-5 goes to vanadium-4 goes to vanadium-5. You've incorporated another oxygen along with the vanadium, so it's VO2, and that leaves 2 protons around. Okay, so this maintains the charge balance. 1 electron has gone away through the wire, and now you have this VO2 plus in the solution and 2 protons. At the other side, the electron comes along, and what happens? Well, vanadium-3 plus goes to vanadium-2 plus. Okay, so you have to remember that always any electrolyte has to be locally neutral. So if you change vanadium-3 plus to vanadium-2 plus, either an anion has to move to the left to maintain charge neutrality, but it can't. It can't move through this Nafion membrane. It doesn't conduct anions. So a proton will move through the membrane to maintain charge neutrality, okay? So there's proton transport happening across this membrane during the charge of the cell. And if you discharge the cell, just watch carefully. All the arrows turn around, that's charge, discharge. You discharge the cell, all the reactions happen in reverse. Okay. Are there any questions about the reactions that take place here? Like, I have a very, very hard time being a very simple-minded person unless I write down a picture of what happens in a vanadium, in a redox flow battery, not necessarily a vanadium redox flow battery. Unless I write down a picture that shows me the half cell reactions, any other ions that are created, and what is transporting across the membrane during operation, I don't understand the cell. Unless I can draw a picture like this, I don't understand the cell. So
Jeff,
there's a lot, yeah.
do you have to use sulfuric acid, or can you use any source of protons in these cells?
I don't know. But sulfuric acid is the cheapest acid. So that's probably why it's used.
Okay.
I think it might also depend on the stability of these vanadium ions at different oxidation states, and so sulfuric acid might be a good compromise.
Yeah, could be the case. Anyway, so if you can't write down a picture of what's happening in a flow battery that's sort of like this, I don't think you have any hope of understanding it and what could go wrong with it. So on your homework for flow batteries, you know, there's all kinds of crazy flow batteries that involve ions like cerium, and there's even a plutonium flow battery that's been proposed, if you can believe it. So on your homework, when you get one for flow batteries, I'll be asking you to draw some pictures like this and then calculate what the full cell voltage should be based on the half reactions that occur. Okay, so this is a good place for us to stop for today based on the time. So if there's any questions about flow batteries, it's a good time to put them forward.
I have a
Jeff?
quick question.
Go ahead.
So I understand why you contain more of the sorry, I just got a notification there. I understand why you contain more of the electrolyte and flow it through, but I'm wondering if there is any other reason why it has to be in motion that I'm not understanding.
Oh, well, it has to be in motion because all the chemicals out in this yellow tank here, nothing would ever happen to them unless they pass by the electrode. They'll never get oxidized or reduced unless they can exchange charge with this porous carbon paper.
Yes, but why couldn't you have the tank surrounding the inert porous electrode or cathode?
Oh, well, then you have too much distance, right? You have to worry about you don't want the distance between the porous electrode and the fluid to be very large. Otherwise, then you're diffusing through the electrolyte over large distances, which we know is a slow process.
That makes a lot of sense. Thank you.
Okay, there was another question, I think.
So this current feeder, is this similar to the current collectors in the lithium-ion cells? Because this are only the fixed parts that collect currents. I think the active materials are constantly flowing, right?
Yeah, that's right. This is just a wire, just like a tab in the lithium-ion cell. Yeah, and the reactants are always flowing through this system, round and round.
Okay.
So what limits the lifetime of these cells? Do you eventually start losing some of your vanadium with every cycle, or does the Nafion membrane get blocked after some number of years? Like, why do these cells die?
Well, I will come to a few of the reasons for why these cells die in the first half of next day. And you'll see that there are some issues. And one of the issues you can imagine is the fact that you aren't in the electrochemical stability window of water, right? You're slightly shifted down. So you've got the possibility for hydrogen evolution going on at one electrode. And then there's some more insidious things that happen besides that also. I'll come to that.
Hey, Jeff. So
yeah,
the energy efficiency of these batteries is mostly due to the pump that's used and that requires energy?
It's partly due to that, but also there's over potentials on the reactions that take place at the electrode surfaces. So the higher the current density that you run, the bigger over voltages you get. So that means there's just an IR drop both in the positive and in the charging and discharging direction. And we'll come to that also. We'll see some discharging and charging curves for these redox flow cells that have been collected at different current densities, and you can see, wow, there's quite a big difference between charge and discharge. But
Jeff,
yes, yeah,
sorry, yeah. Since only proton is exchanging here, so can we use different elements on both sides? Like,
yes. Yes, you can pick whatever you want for the pozolite and the negolite, or the catholite and the negolite. They can be whatever you want. And that's why there's so many varieties of redox flow batteries around. People have tried virtually everything on the left and virtually everything on the right.
yeah, and if the redox reaction has like more than one electron change, would that like increase the energy density? Or
Yeah,
I
if
mean,
you're able to access more than one electron per molecule, and if the redox potential doesn't change so much, then that's a good thing. But in the vanadium case, you know, when you go from 4 to 5 and 3 to 4 and 2 to 3, you know, you change the redox potential by, I don't know, like 0.6 volts every time. So it's difficult to access more than one of them and still make a reasonable cell.
I see. Thanks.
Hey, Jeff, by any chance, do you know if the startup Form Energy is using this technology?
I don't know what Form Energy is doing. I think, didn't Form Energy start by saying they were going to make a sulfur-based redox flow battery?
Okay.
I can't remember what they're stealth, right? Nobody knows what they're doing. But they're hiring. If you want to work there, I just got an email. They're looking for people now. I sent it to my group the other day. All right, well, it sounds like we've exhausted the questions perhaps. But it's clear there's some interest